In lesson 2, we're going to look at more quadratic functions, but now we're going to move them around and see how it changes our parent function x squared. So if we have x squared, hopefully you can pick out from this screen which one is x squared. We know that it starts at 0, 0, and so we would say it's probably this red one here. Now, our next guess here, if we're looking for x squared minus 4, notice that our parent function x squared is having some addition or subtraction after it. Maybe you can look over here and try to guess which one you think is blue, purple, or green. Now the numbers hopefully gave you the hint. If you think about where this is crossing here, between 2 and 4, it'd be a 3. If you said that this one was green, you've got it. And the minus 2 for the purple here, down there, there would be your purple. And that leaves our blue one with the minus 4. Simple as that. You've got your x squared graph, and our parent function can be transformed vertically. A translation, that means moving up and down by adding or subtracting a number at the end. But moving up and down doesn't get all the fun of vertical movement. We can also move left and right. Now, it's a little trickier to find it, but let's look for our parent function x squared. If you said it's the red one, you're probably not surprised that, first of all, it's the same color as the last slide, but you noticed that it started at 0, 0. I want to point out real quickly also that there is that 1 in front of there, as we talked in the last video, if you watched it. That means it goes to the right one and up 1. All these graphs from their vertex still go over 1, up 1. The graphs have not gotten skinnier or wider. They're just moving left and right. So now we notice there's a minus 3, a plus 1, and a minus 5 inserted inside with the x before we square it. It's always possible to plug in a number for x and make a table of values to check. Let's see if we can notice a pattern. Look at where these graphs are hitting the x-axis, which way they're moving and how much they're moving, and see if you can match which color is which. See if you got it right here. We have black moving to the right 3, and green moving to the left 1, and blue moving to the right 5. Now, it might feel a little bit weird. Luckily, the numbers could give you a hint, but you might say, how come there's a minus 5 here, and it moves over to the right 5? Well, think about it. If this coordinate is 5, 0, that means x is 5. If we put a 5 in here, 5 minus 5 makes 0, and 0 squared makes 0. You have to put in the opposite or the opposite value to make this become 0, and that makes it an x-intercept. So keep in mind, let's say if I said x plus 7 quantity squared, can you think of which direction that one would move 7 if we compared it to its parent function x squared? Because the 7's inside the parentheses, we know it's moving left and right. And if you said 7 to the left, you're correct. Plus 7 makes you think right, but remember, 7 to the left would put it at a negative 7, and that would make 0. This is our basic transformed quadratic function, okay? And so this k value shifts it up and down. I think of it as a kangaroo who jumps up and down. That is your vertical translation. Bad spacing here, sorry. And this h, this makes more sense. It's a horizontal translation. Translation just means to move, so it means we're moving the graph. And so horizontal would be left and right. Now, it is important to remember that this is going to be your opposite. It's going to make you feel opposite. When you say if it's a minus 2, it's going to move to the right 2. We didn't see any graphs in this section with our a value changing, but remember this is your, it makes it wider or narrower. And so we don't think of that as a translation. This is more of a stretch, or a dilation maybe, but we'll call it a stretch for now. So again, normally there's a 1 here, and our parabola would go over 1, up 1. But if that number is different, it could flip it upside down if it's negative, or it could have a steeper or flatter slope. Let's try one of these to put it all together. So if I look at part A, I think the most important thing you can define first is your vertex. Remember, our original graph, parent function x squared, starts at 0, 0. This plus 1 tells me to take my parent graph and move it up 1. And this minus 2, so this would say to go up 1. The minus 2 tells us to go to the right 2. So I start from 0, 0, going up 1, right 2. There is my new vertex, and I'm going to give that coordinate a 2, 1. Notice how you can see those numbers in your equation. You don't have to think about what it looks like on the graph. Now, when we draw a parabola at the vertex, the line of symmetry always, or the axis of symmetry always goes through it. So I know that this is going to have an axis of symmetry to cut right through this vertex. Therefore, it is at the x value of 2. We always write our equation for the axis of symmetry with an x equals, because that's the value where the line would be drawn. Now, from here, I see a negative. This means it's going to open down. It's going to be a frown, if you will. So I'm going to go over 1, but instead of going up 1, like our parent graph would, I'm going to go over 1 and down 3. Because parabolas are symmetrical, we can do this on both sides. And for now, this is enough to graph the sketch. Sure, you could plug in more points and get a little bit more accurate graph, but as long as you label the vertex and show which direction and how much slope that a value gives it, you've graphed your function.